All right, hello, this is John Hearn. We'll be looking at some old test questions for rotational motion, and we're going to work through these. If you haven't had a chance, go ahead and attempt these problems on your own before you watch the video. All right, so this first one, a 300-gram block on a 60-centimeter long string swings in a circle on a horizontal frictionless table at 50 RPMs. What is the tension in the string? All right, so let's go ahead and sketch out just a quick schematic of this. So let me grab my pencil. All right, so we're going to need a 60-centimeter long string. So let me draw that. So there's a 60-centimeter string, and then we're going to have a block here at the edge of it. All right, and this is going to go in a circle. All right, so let's illustrate the forces and motion. So just for the motion, let me draw a circle. So there it goes right there. So that's going to be the motion of it. This right here in the middle is the pivot point. We can draw our forces that are exerted on this. Let me put that in green. So let me draw. Now we're going to draw the free body diagram. So there's only one force acting, and that is tension. Now there are two other forces acting. So this is tension. There are two other forces acting, but those are in the vertical direction. There's gravity straight down and the normal force straight up. Those don't affect the motion of the block. All right, and so then let's also illustrate the velocity vector. All right, so the velocity vector at this point is straight up. This is the velocity vector. And this is the tangential velocity vector, which of course is constantly changing as it goes around, but the tangential speed is not, so that's constant as it moves around. And so now we need to set up Newton's law of motion. And so we're going to write the sum of the forces, okay? And now let's write out the sum of the forces. We just have tension. And we'll let this be the positive direction, so we let the direction toward the center of the curvature be the positive direction. And that's the only force acting. And then there's the other side of the equation, which is mass times acceleration. I'm going to put a little subscript c here because this is centripetal acceleration. And so now we've got Newton's law of motion. Let's go ahead and, as we've been doing, write out some of our givens. We know the mass. The mass of the block is 0.3 kilograms because it's 300 grams. The radius of curvature is 60 centimeters, so R is 0.6 meters, and that's this distance right here. All right, and then the angular speed is 50 RPMs, that is omega. All right, and then we're asked for what the tension is. Okay, so over here on the right side of the equation, if we recall, the centripetal acceleration is related to the tangential speed. By Vt squared over R. So once we know this, we can plug it in here. And then all we need is a relationship between Vt and omega. We also know that. Vt is R omega, and we can plug this in here and plug this in here to get an equation that relates tension to the given quantities. So tension equals m times r omega, the quantity squared, over r. And so this is r omega is going into vt squared, so that's r omega squared. And then vt squared over r is going in for centripetal acceleration, and so this gives us our centripetal acceleration. One of the r's cancels, so we can simplify this to m r omega squared, and then plug in what our given quantities are. M is 0.3 kilograms, r is 0.6 meters, and omega is 50 RPMs. And I'm going to go ahead and tuck in the conversion factor right here. So 1 revolution is 2 pi radians. And then 1 minute is 60 seconds. That entire quantity is squared. Okay, so we have to square everything because it is omega that's squared, which we got to put the conversion factor in there. So once I crunch through the numbers, I got 4.93 newtons. All right, so there's our answer. All right, let's move on to the next problem. All right, so in the next problem, we've got a 1.5 kilogram, 20 centimeter diameter turntable, rotates at 90 RPMs on frictionless bearings. 2 540 kilogram blocks fall from above, hit the turntable simultaneously at opposite ends of a diameter, and stick. What is the turntable's angular velocity in RPM just after this event? All right, and so what we've got here is our turntable. Let's just sketch this out from sort of the side. So this is the front here. And then that's the back there. Okay, and it is turning about the center, like this. And then there's going to be 2 blocks that are dropped and placed on opposite ends of the diameter. Here's 1 block right here. Put 1 here and 1 here. Okay, so this is this problem. If you recognize it, we're conserving angular momentum, and we want to know what is the angular velocity just after this event happens. So let's list out what our givens are. We're given the mass and diameter of the turntable. So the mass is 1.5 kilograms. This is for the table. I'll put a little subscript T here for table. And then we're also given the diameter of the turntable. So that means the radius of the turntable is 0.1 meters. So we can label that here. All right, so that's 0.1 meters. And then we also know that the initial angular velocity is 90 RPMs. And then we know the mass of the 2 blocks. So the mass of a block, we'll put a little subscript B here for that, is 540 grams, or 0.540 kilograms. And their location is at opposite ends of a diameter, just like we sketched out here. The blocks are combining with the turntable at 1 radius, so that's at 0.1 meters. Okay. We also know that the turntable is a disk, so we need to know what its moment of inertia is. Moment of inertia of the table is 1/2 mr squared. And then the moment of inertia for the blocks, for each block, for one block is m r squared. Okay, so put little subscripts here. This is the mass of the table. This is the mass of the block. All right, and let me see if I can get this in a little better focus. See if that's a little better. Okay. All right, so we need to know the initial angular momentum is equal to the final angular momentum. So that's what, this is the conservation equation that we need. So initially it is I initial omega initial equals I final omega final. Right, so initially it's all the table. So this is IT, that's omega I, which is right here, 90 RPMs. And the final, I final, is the combination of the turntable and two of the blocks, because there's two of them that are dropped. So we can solve this equation for the final angular momentum. And plugging in the actual equations for the moments of inertia, we've got 1/2 mt r squared over 1/2 mt r squared plus 2 times mb r squared. Now, if you notice, all of the r squareds actually all cancel out, so we don't actually need that in the we don't actually need that information, so we can cancel it out because it's in every single term, and then plug in what we're given here. We've got 1/2 times 1.5 kilograms times 90 RPM over 1/2 times 1.5 kilograms plus 2 times 0.54 kilograms. Notice that we don't need to change the units of this because we're asked for the angular velocity in RPMs. So we can crunch through these numbers, and let's see, I got 52.3. RPM. Let's box that in and move on to question number 3. All right, so a seesaw has a length of 10 meters and a uniform mass of 10 kilograms and is resting at an angle of 30 degrees with respect to the ground. So this is the figure right here. The pivot is located at 6 meters. What magnitude of force needs to be applied perpendicular to the seesaw at the raised end so as to allow the seesaw to barely start to rotate? All right, so we're going to just sketch this out a little bit larger. So let me draw a horizontal line here, just so that we can get that. And then let's measure out 30 degrees. All right, and then we're going to draw this to be 10 centimeters long. And the midpoint is going to be right here, and the point of the pivot point is right here. Let me put a dot there, so that's the pivot point. This is 30 degrees. All right, let's label the force vectors that are acting. So we labeled this is the midpoint, and the midpoint shows where gravity is acting. So remember, gravity acts in the midpoint, at the midpoint of an object. So there's gravity acting. And then there's going to be a force that is acting perpendicular out here. So let's put that. We want to know what is this force so that it just begins to start rotating. All right, let's label a few more key dimensions. This is 1 meter here. So that's 1 meter. And then this is 4 meters. Okay. And then this angle right here, this is 60 degrees because this is a 30, 60, 90 triangle. All right, so now that we've got a nice drawing, we're ready to write in Newton's law for the torques. All right, and we'll just let this be the positive torque direction with this force. So this force is acting at a right angle with respect to the radial coordinate. So r cross f is just r of the 4 meters times f. And then this one right here is in the opposite direction. It's going to be a negative torque, and that's going to be the 1 meter times mg times the sine of 60. And all of this needs to be greater than 0 in order for it to just barely start to rotate. So we'll just set it, we'll solve for this, and whatever force we get, that's what we'll go with. All right. We know, we already labeled all the givens. This is 4 meters, this is 1 meter. The only other piece in here is the mass, and the mass is 10 kilograms. So let's solve for the force. So the force is going to be R1 mg sine 60 divided by R4. And then we can go ahead and substitute in everything that we're given. R1 is 1 meter, the mass is 10 kilograms, G is 9.8 meters per second squared, and then this is 4 meters, so we're going to get the force, and this is the minimum force that is needed, is... I already crunched the numbers somewhere. It is 21.2 newtons. Okay, and so that would be the force required in order to just get the seesaw starting to rotate. All right, number 4, a block of mass 3 kilograms slides down an inclined plane at an angle of 45 degrees with a massless tether attached to a pulley with a mass of 1 kilogram. So this guy right here has 1 kilogram of mass, and this block is 3 kilograms of mass. And the radius of this is 0.5 meters. Okay. The pulley can be approximated as a disk, so we also know I equals 1/2 mr squared. The coefficient of kinetic friction on the plane is 0.4, so mu is 0.4. What is the acceleration of the block? Okay, so in order to help us, we're going to redraw the block and the pulley. Let's draw the block first. Here, let me get just a quick 45-degree line here. Okay, and so here's the block. And we need to draw the free body diagram on this block. So we're going to draw the normal force. So here's the normal force. We also have gravity acting straight down. And this is the mass of the block, which will give it a subscript B. And then we have tension going straight up the incline. And then we also have friction, and friction opposes the direction of motion, so we also have friction heading straight up the incline like this, because the acceleration is down the incline. Okay, so this is the free body diagram for the block. And then let's draw the free body diagram for the pulley, which is somewhat simpler. Let's draw a nice big pulley. There we go. And it doesn't actually matter where we draw the force, but we'll try to draw it at a similar angle here. This is the tension. Okay. And there are some other forces that are acting, but those forces are acting at the center of the pulley because there's gravity acting in the normal force, but neither one of those apply any torque. This is the only force that is going to apply a torque to the pulley. Okay, so now that we've got a couple of nice free body diagrams, we're ready to write down Newton's laws of motion. Let's do it for this one first. We need to break gravity into its two components. So remember, we're going to let this be the y direction, and then this is the x direction. Okay. All right, so the sum of the forces in the y direction. Now we've got the normal force. And then we have the mass of the block times gravity. And remember, this is theta, which is 45. This is also theta. So this is going to be mg times the sine, the cosine. The cosine of theta, and this is going to equal 0 because there's no acceleration in the y direction. So this tells us that the normal force is mg cosine theta. And then we have the sum of the forces in the x direction. So I've got mg sine theta in the positive direction. And then I have tension and kinetic friction in the negative direction. This is going to equal mass times acceleration. Now these are all masses of the block. Let me put a little subscript b here, and here, and here, and here, because then we're also going to have the mass of the pulley when we analyze its motion. But if you notice here, we can go ahead and put in friction. Friction is mu times the normal force. And then we get this equation for the motion of the block. There are two things we don't know the tension. There are two things we don't know: tension and acceleration. So we're going to need to look at the pulley in order to find the rest. So we're going to allow the torque to also be in the positive direction. So this is going to be R cross T, which is just R times T. And this is equal to I alpha. All right, so R is the radial coordinate on this, which is 0.5 meters. And then I is 1/2 mr squared. All right, so we can solve for tension here. And we know that alpha equals A over R, where A is the tangential acceleration. So I can put that in. All of my R's cancel. I divided R over, so all of my R's cancel. And I'm left with the tension equals 1/2 m subscript P times A. Right? So I put a subscript P here because this is the mass of the pulley. And that's important because it's different than the mass of the block. So now we can take this and plug it in right here for tension. And we just have two equations with two unknowns. All we need to do is solve. So we have one equation now with one unknown, and then we just need to plug in everything and solve it. And when I solved this, I got an acceleration of 3.56 meters per second squared. All right, last question. A solid cylinder of radius 10 centimeters rolls down an incline with slipping. The angle of the incline is 30 degrees. The coefficient of kinetic friction on the surface is 0.4. What is the angular acceleration of the solid cylinder? What is the linear acceleration? So let's just draw a quick diagram with a 30-degree slope. So here's the slope. Here is the cylinder. Okay, and the cylinder is going to be moving down this way. This is acceleration. Okay. So let's draw the free body diagram on it. I have the force of gravity acting straight down. We've got the normal force acting perpendicular to the surface. And then we have friction acting like this up the incline. And this angle is 30 degrees, which means this angle is also 30 degrees. Okay, so there's only one force that's applying a torque, and that is the kinetic friction. So let's analyze the motion and find these two. We'll allow the y direction to be aligned with the normal force. Which tells us what the normal force is. All right, and then let's add up the forces in the x direction. And this is what we get. Now we're given the coefficient of kinetic friction, mu equals 0.4, right? And so we can find out, because we know the normal force, what the kinetic friction is. All of the mass terms cancel. And then all we're left with is the acceleration. And the acceleration for this is, I got 1.51 meters per second squared. Notice that because this is sliding, it is slipping, that we actually didn't have to look at the rotational motion to solve the problem, at least the linear acceleration part of the problem. And that's because we know what the kinetic friction is. We can also now look, we need the angular acceleration of the solid cylinder. Because it is slipping, the angular acceleration and the linear acceleration are not equal, right? Because it's slipping. So we just have to solve for Newton's laws for the rotational motion. So there's only one force that is applying a torque, and that is kinetic friction. So this is going to be R times Fk equals I alpha. And we're solving for alpha. We actually know everything in this equation because we know Fk is mu times the normal force. We got that right here. And we also know I, because this is a solid cylinder. It's a solid cylinder. We know I is 1/2 mr squared. And then we know everything in this equation. We know R, we know M, and we know G. So we can solve for alpha. And alpha for this problem is, I got 67.9. radians per second squared. And there we have it. All right. Have a good day.